Hey guys, today I'm going to be going over Sickle, a payload development framework that I designed for both red team operators and exploit developers. In this presentation, I'm going to be showcasing how you can integrate Sickle into your workflow when working with other C2 frameworks. More specifically, we're going to be targeting Windows and Linux environments since these tend to be the more widely adopted operating systems amongst different organizations. And of course, it goes without saying, but I do want to start off with a disclaimer. Since we're going to be going over hacking techniques that can be used to gain unauthorized access onto computer systems, I want to emphasize that anything you do with this knowledge, you're going to be held completely responsible for, and so always make sure you're operating within the confines of the law. In addition to this, any opinions expressed in this talk are my own and don't represent those of my employer, past, present, or future. So, with that out of the way, my name is Milton Valencia. I'm a principal engineer here at HPE, and I'm working with the Offensive Security Special Ops team. I've also had the opportunity of working alongside other Fortune 500 organizations, such as Costco Wholesale. And I've been doing this for about 7 years, but I really got started as help desk working with Miguel Rodriguez. So shout out to Miguel and shout out to anybody currently working help desk. I tend to move around a lot, so I don't want to necessarily claim that I'm from a particular location. However, I am an American y también soy salvadoreño. So for those of you that may not speak English as your first native tongue, I also release my publications in Spanish. And you can find those at Wetwork7 on X, Blue Sky, and YouTube. And of course, in addition to this, any open source tooling or any techniques that I may be publishing, you can also find on my GitHub at /wetwork. So pivoting back into the original talk, what is Sickle? Why did I design it? And why should you be interested in it? So this was originally a big script that I made to reverse engineer different shellcode stubs that you find out on the market. And more specifically, I was developing this tool because when I got into exploit development, the main correlated similarity I found amongst all of these POCs was shellcode being generated by a tool you may be familiar with known as MSF Venom. Of course, I never want to have dependence on any particular tool, and so I wanted to understand how these payloads were working and how they were even being generated. And after years of research, I decided to expand Sickle into a framework that also supports payload generation. And so the core functionality has been kept under the development modules section, which you can see here. A couple of them are diffing, testing, and formatting the shellcode into different languages. And the architecture support is currently x86, x64, AR64. And if you were familiar with the old previous tool or the earlier versions, you may see that the architecture support has slimmed down. This is intentional just because I want to make sure that anything that I integrate into the framework has been fully tested by me or other operators that are working with respective architectures. And even though it's not listed here, there are a couple payloads that do work on Android, and due to time constraints, I won't be able to go over them today, but it's just something to keep in mind. Now, the actual modules, the way they've been made, I've tried to make a Frankenstein of C, Python, and assembly in order for you, the operator, to be easily able to identify the different types of variables and structures that are normally used by these shellcode stubs. And so I do believe the best way to learn this type of information is by actually doing it. And so let's go ahead and jump straight into the demo. I'm going to go ahead and turn off my camera just because I want to make sure that you guys are able to completely understand everything that's going on the screen, and I don't want to get in the way of anything. So let me go ahead and disable the webcam. And we're going to go ahead and launch Kali Linux. So what you're looking at here on the right-hand side is H. Victor's GitHub. I wanted to give him a shout out here because I'm actually using his intentionally vulnerable application, Target Xserve X64. And we're also going to be using his proof of concept in order to demonstrate how you would take another person's proof of concept and then adapt it to use Sickle instead of whatever shellcode they actually decided to use. So I'm going to go ahead and close this. And let's go ahead and copy target serve into poc.py just so we don't end up doing any modifications we can't undo. I'm going to also open a tmux session just so that I can work with multiple sessions easier. So I'm going to do poc.py here. And basically what we're seeing here is that there's a host, a port, and shellcode. These are normally the main things that you'll look at as an operator because the rest, even though it is important to know, perhaps for the given operation, it's not entirely necessary for you. So we can see that he used MSF Venom to generate the shellcode. And in order to see how we would generate something similar in Sickle, we can actually open a new session, and I'm going to go ahead and make it larger and do Sickle tac L. This is going to give us a list of everything that Sickle supports. including the payloads, the architectures, modules, and formats that are currently supported by the framework. Now, in this case, we're only really interested in the payloads. So I'm going to go ahead and clear the screen and do Sickle, tac L, payloads. And so here it gives us only the payloads since that's the only thing we're interested in. And we're going to be looking at the virtual alloc exec TCP. So once again, I'm going to do Sickle, tac P, the payload we're going to be looking at. And I'm actually going to do a tac I. This is going to give us information on the payload. So here we can see that this is a userland payload. And this is a shellcode loader. So essentially, this is going to be a multi-stage payload where our initial stage is going to execute, and then it's going to reach back out to another handler and get the second stage in order to execute and achieve our ultimate goal. Which in this case, we're going to be running a ransomware emulator, a completely custom software that I wrote during red team operations. So it also mentions that the handler can be as Sickle as using Sickle itself alongside Netcat, and so that's exactly what we're going to do. I'm going to go ahead and bring this to the side, and we're going to get our IP since this is where the second stage will be retrieved from, and we're going to copy and paste exactly what's shown in the example. So in this case, it's lhost. We're going to change it to what our lhost is. We're going to also use lport 1337 because why not? And in this case, we wanted to match the exploit we're working with. So we're going to change the format to Python 3 instead of C. And we're going to change the variable name to shellcode since that is the variable name that hvictor used. And that should be everything we need. We can see that we were able to successfully generate the shellcode with it being under 500 bytes. I'm not going to worry too much about null bytes just because in this case we're exploiting a 64-bit application. And from my experience, we don't really need to worry about null bytes too much when working with this architecture. So we can go ahead and copy and paste it here. So we're going to get this shellcode and paste it. Now, I want to note that here you can see that the original command that we used to generate the shellcode is immediately listed as a comment. So that if you're handing this exploit over to a different operator, maybe you're exploiting another system that has the same configuration, they'll be able to quickly adapt it to whatever their needs may be. Maybe they're using a different C2. And of course, the size that the payload uses in order for you to have the ability to use a different stub if you need to remain within the confines of that particular space. So I'm going to go ahead and close this since we're done generating the shellcode. Or rather, I'll go ahead and leave it open for now since I do actually want to reference that example, and we can even add a tac I here. We don't necessarily need to backspace all of that. So I'm going to go ahead and make this like this, and the next thing we're going to do is I'm going to run RDP against the actual machine. And the reason I'm doing this is just so that you can have a visual representation of what's happening. So of course, this isn't any hacking. This is just logging into the machine so that you can see visually what the user would see during the exploitation, if this was a real scenario. So I'm logging in there. We actually get the IP here from the RDP script, and since we were able to log in, I'm just going to go ahead and do that and change it here on the host. And the port seems fine, 9090, since that's the vulnerable application that hvictor wrote the port to be on. And at this point, we want to set up a handler. And the reason we want to set up a handler is because this is what's going to be distributing the second stage payload. So let's go ahead and go back to this window here. And we can see that the example shown is here with Netcat. And in this case, it's referencing another payload within the framework, which is the reflective PE loader. Now, because we're working with the custom framework, I actually have to go into the framework that we're going to be working with and take a look at the payload. So this payload here is 160,000 bytes. Now, I want you to really think about the difference between 500 and 160,000. Clearly, this is why we want to go ahead and use a staged payload. So I'm going to copy this exact syntax here. I don't need to type it out. And since I've ran it before, Kali actually has autocomplete enabled. So I can see here, we're going to be saying sending UFO. We're going to be putting it in raw format since we want to send this all in raw binary data, like just the bytes, over port 1337, since that's what we set it when we generated the shellcode. So we have everything we need here. We can go ahead and launch that and go back to this window here. I'm going to close this since it's no longer necessary. Now, going back to this, I'm going to go ahead and launch the intentionally vulnerable application. We can see that it's here running on port 9090, just as the exploit suggested. And I'm also going to open up the Explorer window because I want you guys to see the ransomware attack actually happen. Now, because this is emulation software, I'm not going to be deleting the actual original files. And I'm mainly doing this to emphasize that, of course, we're ethical actors and we never really want to harm a system. Now, I programmed it right now to only work on this directory, so this is where we're going to see it. Now, let's go ahead and launch the actual C2. So going back here, I'm going to go to the C2 server. Oh. And we're able to launch Ophanim, which is going to be our C2 server. Here you can see that it's listening on port 443. So essentially what's going to happen is the initial payload is going to land. It's going to call back our handler. Our handler will send UFO.exe and reflectively load the ransomware in memory and gain a reverse connection to the C2, which in this case is Ophanim. So let's go ahead and check the exploit once more. We got 91.149 and I believe that is yes, and then we got port 9090, and let me double check that we did in fact change the shellcode. Yes, we see Sickle. Gonna write it just to be sure. And now we're ready to launch the POC. So fingers crossed. Let me make sure it's running actually. Okay, yes, it's running. So let's run it. Here we go. Is it running? Might have to run it again. Let's see. You know how live demos go. Okay, there we go. We can see we get the connect back. And all we need to do is hit Control-C, and this will essentially send the payload over netcat. Nice. We can see that we were able to successfully get code execution. We can see that the ransom was successful and that we were able to encrypt the files that were precious to this user. And if we look at the README on the desktop, we can see that they got the ransomware letter. In this case, it's Black Hat 2025. Going back to C2 server, this is what the attacker would actually see. We can see that the connection was established, encryption was performed with the password Black Hat 2025, and the attack was completed. If we go ahead and click on this node, we can see that the target IP address here was the one that we were successfully able to compromise, the user that was compromised, the password used, and the number of encrypted files. So that pretty much concludes the Windows demo, but I'm going to go ahead and jump straight into the Linux one. All right, so what you're looking at here is Hash's GitHub. In this case, it's /Carlos Slack, and he is the author of COVID. And so this is what we're going to be demonstrating to do the rootkit. So I'm going to go ahead and close this. And I'm also going to go ahead and open another session. It's red on purpose because this is going to be just like the RDP session. We're going to go ahead and log into the actual target machine on this window. But before we do that, let's take a look at the exploit we're going to be working with. So in this case, we're going to be working with the exploit that I wrote actually, and this is for an intentionally vulnerable application that I also wrote since I couldn't find one in time to use. And so in this case, we're using the memfd reflective elf TCP. Now this is a similar scenario to what we saw with Windows where we're going to be loading a package executable, but in this case, since we're working with Linux, it's going to be in elf. So actually, let me open another session here and cover up this red one just so we can get more information on this payload. So we're going to do attack I. And so we can see here that just like the Windows payload, we're going to be piping a payload into netcat, and then it will be sending the second stage over to our target host. So this is pretty simple and self-explanatory just as the last one. So I'm going to go ahead and close it. And let's take a look at the R host here. And just because of dynamic name resolution, or not name resolution, DHCP, the IP tends to change. So let me go ahead and check what it is. It's right now it's sitting at 152, and you can't see this because the virtual machine is running on the other window. So we're going to do 152, and we're going to go ahead and SSH into the vulnerable user that's going to be running the application. So once again, on the right hand side, this is actually the user's machine. We're going to elevate to root. And the reason we're going to do this is because I want to make sure that we have visibility over all of the processes that are running on the target machine. So here we see the processes running. I'm going to go ahead and start the vulnerable server. Let's see, server, there we go. Okay, so we should see it here. Well, I guess I don't see it, but we should see the process here in a minute anyway. Now, I'm going to go ahead and close this. But the next thing I want you to look at is the DOS powergrid.c here. So this is basically what we're going to be running. I painted the scenario off the matrix, you know, AI and everything trending right now. And so this is what's going to be printed to the screen. And we're basically going to do an infinite loop. And this is just to showcase like a DOS where Trinity, you know, disables the power grid when they're going to go try to save Morpheus in the movie. So going back to the exploit, we did already swap out the payload, so I'm not going to generate it. And just to further emphasize that, we're going to open it again. And you can see here that I already generated it. It's already set to the right L host. L port is 1337. And so what payload are we actually going to be sending? So once again, I'm not going to be going over building COVID, but kvinc_bin, this is actually what's going to be sent over as the second stage. And so to do this is going to be pretty easy. Once again, I'm going to do a tmux session. And we're going to do nc listen on port 1337 and pipe the binary that's going to be doing this attack. Now, once again, I don't have this stuff memorized, so here's my little cheat sheet. This is basically how we're going to be able to connect to the rootkit. Now, to prove that this is actually this isn't already running, I'm going to go ahead and try to connect to the target host over port 999. And this here is the key that I used, or that the rootkit generated when I built it. So I'm going to go ahead and try to connect. Oh, to get to the script, we actually have to go into the repository, go into scripts, and there it is. So we're going to give it a minute here, and it's going to go ahead and connect. And while that's going, let's go back here just so we're ready. So everything here is running good, yes. And now let's go ahead and double check that the exploit is programmed correctly to the target host. Yes. So let's go ahead and run it. But before we run it, of course, we're going to go ahead and stop trying to connect to the back door. And so our handler's up, we're ready to launch the exploit, and we can see on the right-hand side the different processes that are actually running on the target host. So here we go. Strange. Okay, let me go see what's happening here. Try again. Okay, this time we did get the connection. Kind of funny how Windows did that too. And so we're going to go ahead and hit Control C. This is going to install the rootkit. So I got to show the exploit output there. And we can go ahead and close the handler. Make sure this is visible here. And let's go ahead and connect to the back door. Hopefully it did install. Nice. So we are able to connect to the rootkit at this point. And so once again, to further emphasize the example here, we're going to be cding into /bin. And we're going to do this because we're going to be uploading that binary that we previously mentioned, which is going to be DOS. Let me see here. Grep for it. Go ahead and start, or let me get an IPA, DDR show et o. That'll give us that. And so essentially we're going to be starting a simple HTTP server in order to be able to download it, or upload it rather, onto the target host. So we're going to do a wget, and then we're going to do HTTP since we're using the HTTP protocol. And we're going to do the IP here. And we're going to do the name of the binary itself. Nice. So we were successfully able to download it. Now we're going to go ahead and make it executable. And we're going to run it in the background. So hopefully we see it here. Nice. So let me move this more here just so it's easier for you to see. So here we can see that the process DOS power grid is running. So of course we're dealing with AI here. So we don't want the AI agents to be able to see that we're running this. So we're going to go ahead and send a signal to the rootkit to allow us to interact with /proc files. Now I named the rootkit in this case, I believe pipeline monitor. So I'm going to go ahead and send this signal here. I'm going to do a sudo kill tac cont 31337. And so we get this error, which is expected. And if we do a D message, we can see that our rootkit is ready to be worked with. So we're going to do echo, and in this case, the PID, which is going to be, what is it here? 3915. And we're going to pipe it, or let me see here. We're going to do echo, and then we're going to do, echo, the process name, and now we're going to pipe it into /proc/ and in this case, it's going to be pipeline monitor. So once sent, we should see it disappear from the top. So I want you to keep your eye here. Nice. So we were successfully able to prove that we were able to load an entire rootkit with under 500 bytes. And to prove that we were able to execute a rootkit, we were able to hide the process that's currently performing a denial of service attack, hypothetically in this situation, against the AI agents. So let's go ahead and go back into our presentation here with the exploit demo complete. And if it'll let me, okay. So that was a lot to unpack. You know, clearly we were able to do 2 exploitation scenarios rather quickly. So what happened? To recap at a high level, we began by launching an exploit from our Kali machine, which contained a payload generated by Sickle at both Windows and Linux environments. Once executed, the payload then reached back out to the handler, which was also hosted on our Kali machine, and upon doing so, our handler then sent the final stage to be exploited or to be executed, completing exploitation. At this point, our malware is installed and performing whatever actions we wanted it to take. On Windows, we successfully deployed our custom ransomware emulator, and on Linux, we successfully loaded a rootkit. And again, I want to emphasize that this was accomplished under 500 bytes for our initial payload stub. So how can you develop additional stubs for both you and your team? If you take a look at this example, I've removed a majority of the code so your focus can be on the core components of a standard module. Starting from the top, you can see how Sickle offers header imports as modules, and this was intentionally made to mimic your standard include that you would see in a C program as shown on the right-hand side. Looking at the shellcode class itself, you can see that dependencies are automatically taken care of for you once they're declared, and more importantly, mimics how you would visually identify different parameters in C. This makes it difficult, or this rather takes away the difficulty of working with assembly and C and makes it more operator friendly because, as you know, not everybody on a red team could be the reverse engineer. You know, you have guys with different skill sets. And the same can be seen in Linux. So once again, in this example, you can see how the imports directly map from a visual perspective to C, with the main difference here being that the dependencies are no longer DLLs and functions, and instead we're working with syscalls. Of course, this is due to the nature of working with Linux and different operating systems in general. You're going to tend to have different calling conventions and ways of interacting with the operating system. So to address this in future releases, I do plan to implement the ability to dynamically obtain this information. But for now, it's documented in each reverse shell if you're working with a new platform that you haven't with before. So having obtained this high-level overview, how would you then integrate a module that you've ended up building for you and your team into the framework without open sourcing it? Because as we know, some red team operations are so sensitive that we don't necessarily want to share everything that we've written with the world, and it may be something that we just use internally with our organizations. Well, it's actually really easy. You would simply move the payload module or format that you've designed into its respective folder under your .local/share/Sickle directory, and once placed, Sickle will automatically be able to load and run your module. Here on the right side, you can see that I'm running the tree command, and you're able to see a visual layout of where you can place additional modules and formats and payloads. Knowing this, knowing that I would be adding a Windows payload, I went ahead and copied it into the appropriate directory. And once copied, when I ran Sickle again, you can see that I was able to successfully load the shellcode module. And again, any module can be made in this manner. It does not necessarily need to be shellcode. It could be a format. It could be a development module, really however you plan to expand the tool for you and your team. So thank you guys all for checking out Sickle and hearing me out. I really appreciate your time. I want to give a special thank you to Alfredo Pasoli. Although he's not mentioned as a contributor on the actual GitHub page, he's been a huge mentor to me and advancing me and my abilities, and he's given me a lot of input during its development. I also want to thank H. Victor for allowing me to use his intentionally vulnerable application to demonstrate Windows exploitation, and Hash for letting me integrate COVID into the demo. And I can't forget about the Kali team. You guys are sick. Thank you so much for integrating this into the operating system. And last but not least, anyone who's ever sponsored the tool, I really appreciate the support. It really means the world to me that you've been able to believe in this project and help it get to where it is today. And for those of you that have any further questions, feel free to reach out to me. I'm on Discord, and you can follow me on X for any future updates with the tool and anything else that I'm working on. I really hope that I can meet a lot of you at Black Hat 2025, and yeah, thanks again.